In this problem, we want to sketch y is equal to x times square root of 5 minus x squared. We are going to follow the guideline given in the book. So the first thing that we want to actually do is to determine the domain of this function. Because we see the square root here, the domain is whenever 5 minus x squared is going to be bigger than or equal to 0. We factor out the left. So to factor this, we use the difference of two squared. So we set square root of 5 minus x is greater than or equal to 0 to get that x is going to be less than or equal to square root of 5. We set square root of 5 plus x is greater than or equal to 0. And we get that x is greater than minus square root of 5. So the domain in this case is going to be from negative square root of 5 to square root of 5. 2. We want to determine the intercept of this function. So the y-intercept, simple enough, you put in 0 for x. In this case, it's just 0. For the x-intercept, you set the y value equal to 0, and then you try to solve for x. So, either x is equal to 0 or the square root of 5 minus x squared is equal to 0, in which we already solved in the prior problem, meaning this is when x is equal to plus minus square root of 5. Moving on, we want to determine symmetry, if there is any. For symmetry, we want to consider f of x is equal to x times the square root of 5 minus x squared. And we also want to consider what happened when we put in a negative. Instead of having just x, we put in a negative x. Well, this turned out to be x times the square root of 5 minus x squared, which is just the negative of the function f of x. And keep in mind, when f of negative x is equal to f negative f of x, this is an odd function, meaning reflection about the origin. Next, we want to talk about the asymptote. In this case, we note that due to the fact that we have a bounded domain, and inside this domain is two continuous functions, meaning there are no horizontal asymptote. Because of the bounded domain. And also there are no vertical asymptotes as well, because inside the domain, this is a continuous function. The next thing that we want to talk about is going to be interval of increasing and decreasing, as well as local max and local min. All of this amount to simply taking the derivative of the function. So recall that the function is y is equal to x square root of 5 minus x squared. So we want to find the derivative of y. So y prime is equal to, here we take the derivative by taking the product rule. So derivative of the first term, which is just x, so derivative is 1. 5 minus x squared raised to the power of 1/2 plus, leave the x alone, take the derivative of the second term, 5 minus x squared to the negative 1/2. But for the second term, that's a square root function, so we apply the chain rule. Then we simplify. Let me pull out a 5 minus x squared to the negative 1/2. The first term becomes just 5 minus x squared. The second term becomes negative x squared. We simplify. On top we have 5 minus 2x squared. On the bottom we have 5 minus x squared to the 1/2. So here we note that the denominator is only 0 on the boundary. So those give us 2 critical points that we can work with. To find the other critical points, we set the numerator equal to 0. We solve. So x is equal to plus or minus the square root of 5 over 2. After we find all the critical points, we can make a sign chart. X and the derivative of the function. And we draw all of our critical points. So negative square root of 5, positive square root of 5, negative square root of 5 over 2, positive square root of 5 over 2. And we note that since the domain is only from negative square root of 5 to square root of 5, there's nothing to the left, there's nothing to the right. So all we care about is choosing value in between these critical points. So let's pick an obvious one, 0. Put it back into f prime of x and see what do we have. We put in 0 here, we put in 0 there. We get a positive number. Then between square root of 5 of 2 and square root of 5, that is about 2. So we can just pick 2. Similarly, we can just pick negative 2 because it's symmetric about the origin. We put in 2 and we get that this is going to be a negative number. And we also get that negative 2 will also be a negative number. And there we have it. We have that the max is at square root of 5 over 2. And whatever the function value at square root of 5 over 2 might be. The min, in this case, note that these are local max and local min, occur at negative square root of 5 over 2, and wherever that might be on the y value. We also have increasing and decreasing interval. Decreasing on the interval where f prime is negative. So from negative square root of 5 to negative square root of 5 over 2 and square root of 5 over 2 to square root of 5 and increasing on negative square root of 5 over 2 to square root of 5 over 2. All right. With that, we can pretty much tell what the graph is going to look like. However, we want to have one more points. Those are going to be the points of inflection. So these points of inflection will be the second derivative. Note that we already have the first derivative as being 5 minus 2x squared all over 5 minus x squared to the 1/2. Then we take the second derivative. I'll try to find it by rewriting my function as 5 minus 2x squared times 5 minus x squared to the negative 1/2. Here I'll try to take the derivative by applying the product rule and the chain rule instead of the quotient rule, because I think that's a lot easier to do. So I'll take the derivative of the first term, minus 4x, leave the second term alone, plus leave the first term alone, take the derivative of the second term, which would now then be negative 1/2, leave the inside alone, minus 1 in the exponent, then take the derivative of the inside. Again, I'll try to do some factoring. In this case, I'll factor out a 5 minus x squared minus 3 to the minus 3/2. So for the first term, I will have minus 4x. What is left is going to be 5 minus x squared plus 5 minus 2x squared and negative 2 over 2 just x, and then maybe some simplification of the top, minus 20x plus 4x cubed plus 5x minus 2x cubed on top, all over 5 minus x squared to the 3/2 on the bottom. On top, a little bit more simplification, we have 2x cubed minus 15x all over 5 minus x squared 3/2. Again, we try to find the zero of these, so we simply need to set the numerator equal to 0, and then we solve. So we factor out an x, so 2x squared minus 15 equal to 0. So either x is 0 or 2x squared minus 15 is equal to 0. Well, 2x squared minus 15, that's going to be 15 is equal to 2x squared minus 15 equal to 0. We solve for x. We get x squared is equal to 15 over 2. Therefore, x is equal to the square root of 15 over 2, plus or minus. And now, once more, we make a sign chart. We have x, we have f double prime of x, and we mark down all of our zeros. Or rather, in this case, all of our point of inflection. So negative square root of 15 over 2 on the left, square root of 15 over 2 on the right, and 0 in the middle. So we can simply pick around 1 and negative 1. We put in 1, we get that this is going to be a negative value. We put in negative 1, and we get that this is going to be a positive value. In this case, we note that negative square root of 15 over 2, that is outside of our domain, so nothing exists out there. And same reason, nothing exists out there. So let's take a look at what we have so far. So far, we have domain, symmetry, intercept, local max, local min, increasing interval, decreasing interval, and also concave up, concave down. Just a quick note that from negative square root 15 over 2 to 2 to 0, the function is going to be concave up. And from 0 to square root of 15 over 2, it's going to be concave down. We put all of this together into a graph. So let's mark the intercepts. The intercept is going to be at 0 and square root of 5 plus minus. So right there 0, somewhere around there at square root of 5, and then somewhere around there at negative square root of 5. Let's mark our local max and local min as somewhere around there as square root of 5 over 2. And somewhere around there at negative square root of 5 over 2. And there's a local max somewhere around there, and there's a local min somewhere around there. And then that's really is all we need. We know that the function is concave up from whatever this interval is. So here it's decreasing, and we can also tell that from the first derivative. It's decreasing from negative square root of 5 all the way down to square root of 5 over negative square root of 5 over 2, and then it's increasing up to that point in which 0 is now a point of inflection, which changed from concave up to concave down. And then that's the graph.